webinar. And the demo is not, I'm going to be honest about where the demo is. I think the first half is really good. The second half, where you extract features and use it for a supervised task, I'm going to talk about how I think I'm halfway there, but it's not. Oh, wrong one. Cool. Uh-oh, we're getting started, aren't we?
Oh yeah.
This is happening.
Go back.
Oops. Save.
Hey, good evening. So welcome to the House of Music. And I wanted to, first of all, a couple of real quick announcements. Wanted to thank Spotify for hosting us this month. This is a really awesome space. I haven't been here. And second announcement, we are adding another co-organizer to the Meetup.
Seattle.
You guys might have known Eric Bernardson. He used to work at Spotify, and he spoke at our Meetup several times. He's awesome. He's going to help us run things. And Chris from Spotify is going to introduce the speaker. Enjoy.
Hello. Cool. Yeah, so my name is Chris Johnson. Work on the machine learning team here at Spotify. Thanks everyone for coming out. Two things. One, beer, soda, water, coffee, all that in the back. Feel free to help yourself. We also have quite a bit of pizza. So feel free to grab some pizza, grab some beer. But you're not here for Spotify, you're here for Rajat Arya. He's here all the way from Seattle, works at Dado, and has some really cool stuff to present to us. So without further ado,
All right.
Rajat, take over.
Thanks, Chris. Hey guys, can you hear me okay? Is the mic,
It's on, it just doesn't work super well.
how's this? Is this better? Okay, I'm just gonna eat the mic. It's gonna be totally fine. If you can't hear me, let me know. I can speak up. I can certainly project louder if I need to. Thanks for coming out tonight, guys. I'm sure it's not for the pizza and beer. Hopefully it's because you have lots of log data and you wanna do something with it. So I thought I'd start out by introducing myself a little bit. First and foremost, thank you, Max. Thanks you, Chris. Thanks for Spotify for hosting. I think this is a great space. My first time in this office. It's really nice. If you want to get the slides that I'm going to present today, I've got a URL on the top of this, and I'm happy to share this URL because I only had time to put it on this slide, not on all the rest. If you go here on your phone, you can sign up, and then I'll email you the slides in the next couple days. OK. So again, my name's Rajat. I do product and sales at Dado. And I guess my other claim to fame at Dado is I'm the first employee. My background's not in machine learning. My background's in distributed systems and large-scale systems. So prior to Dado, I was with AWS for a few years. And before that, I started my career at Microsoft. And I worked on Windows for a while. And I think the last product I shipped at Microsoft is called OneDrive today. So I've always sort of been in this large-scale distributed system space. I joined Dado. And for the first year and a half, I focused on our production tools, which I'm not going to talk about tonight, but I think are pretty awesome. And about a year ago, I switched over to this role in product and sales, where now I spend most of my time with customers, helping them integrate our products into their applications. So that's all I'm going to say about myself. If I didn't mention it before, please interrupt me, raise your hand. I want this to be interactive. It's after work. I can't possibly lecture you guys for 45 minutes. So please help me out and make this more fun for me and hopefully for you. How many of you have heard of Dado before? Good. I have nothing else to say. I'm done. So Dado is a machine learning company. We're based out of Seattle. We're in town for a bunch of different things, but one of them is for PyData in New York. And did anybody come from PyData? Is anyone there this week? Couple? All right, cool. We were a company for about 2.5 years. Before that, we were a research project. We started in 2008 at Carnegie Mellon. To explore large-scale machine learning on graphs. We were originally called Graph Lab. So about 2.5 years ago, we became a company, and things have gone really well for us in the last 2.5 years. We have about 50 people on the team today, and I guess a fun fact is over half the team has a PhD. Our specializations vary from databases, distributed systems, visualization, machine learning, and statistics. And we're really focused on making it easy for developers and data scientists to build applications that use machine learning and deploy those applications. So that's all I'm going to say about Dado. The only thing I'm going to mention about our platform is that it can help you through the typical workflow that you go through as a data scientist. But I should first ask, how many folks are data scientists? How many folks are data engineers? How many folks manage data scientists and data engineers? All right, good, good, good. How many folks code in Python? Ha ha ha. Java? Scala? What else? R? Are there some R folks? All right, SAS? Any SAS folks? All right, very cool. Well, I like the fact that almost everybody raised their hand for something, and the other folks are busy eating with both hands, so I'm totally cool with that. So as data scientists and developers, you're typically in this prototyping workflow, and where you're working with data, modeling, and exploring. And so we have tools that can help with that. We have products that can help. So of course, after you have that first model, that's not the end of your application. You want to deploy that model, typically as a real-time service, and then use it for real-time predictions. Take feedback that the model gets as a service, incorporate that feedback to update the model while you're developing the new model, and of course do online model experimentation, whether that's A/B testing or something more advanced like multi-arm bandits. And that's it. That's all I'm going to talk about regarding Dado. Today we're going to talk about log data. So everybody's got logs, right? Yeah. How many of you are using log data for something today? OK. So we're going to talk about frequent pattern mining. And oh boy, let me get out of my product slide. Here we go. So we get logs from everything, right? We get logs from cars now. You can plug in devices to the port in your car and find out all sorts of fun stuff and kind of make you feel like you're a mechanic, because that's basically what your mechanic's doing now. Every device that you have is submitting data, is sending data, and is generating logs. And we're supposed to do something with those. We're supposed to find insight in them. And then, of course, we're supposed to profit and kind of look like this guy, who looks pretty happy for a stick figure guy. But there's usually a challenge with log data. And the challenge is you don't actually, it's unstructured, it's usually really messy, and it's pretty hard to know what is going on in your log data. How can you leverage that for something? So this area is pattern mining. And of course, we all know that logs are everywhere. I do happen to like this actual picture of logs to just hone in on what we're talking about. And so using machine learning with your log data typically falls into a few areas. So anomaly detection, what's common, so I can now identify what's uncommon. Pattern detection, what is common in what's happening with my application or with my users. And then visual analysis. If I can group things together that are common, then I can help understand all the things that are happening. So far, so good, guys? Yeah? No one stopped me, no questions so far. You guys are all still here, right? OK. So let's take an example. Let's try and ground this in a real example. We're from Seattle, so we like our coffee. So my example is going to be about a coffee shop. That's the data set I'm going to use, is effectively a bakery data set. So what do coffee shops serve? They serve coffee, pastries, other things that you may want to have with coffee, maybe cookies. Are cookies pastries? What do you guys, cookies and pastries, is there a difference? I don't know. OK. Well, donuts, cookies, pastries, are they all the same? I don't know. They're all delicious. So what is the log data that a bakery or a coffee shop might have? It's probably got receipts. Maybe they're electronic, but maybe not. So what can we do with this receipt data? Well, so this would be the logs that a coffee shop might have, would be receipts. They might look like this. So what you see is, let me see if I can do this with the mouse. OK, we'll do this with the mouse. Uh-oh. Oh, no. I'm going to get a pointer. That'll make this better. So what you can see is each item that's sold comes with a receipt. And so you have a receipt ID, and you have a OK. So you have a receipt ID. So you can see this is an item that was sold, a ganache cookie. I don't know what this is. If somebody knows what a ganache cookie is, please tell me. I have no idea. But I know what apple pie is. And so apple pie and a ganache cookie were sold together. They're on the same receipt, same date, by the same employee, in the same store. 1 ganache cookie was sold, and 5 apple pies were sold. Does that make sense on this data set, what you're seeing in the logs? So each item sold has a receipt and an item. So we might want to find out what items were typically sold together or bought together. So if you got coffee, did you also get a muffin and a Danish? Or if you bought, I guess one of these is coffee, one of these might be tea, you got a cookie. And this is frequent pattern mining. So this is the thing we're going to talk a little bit more about today. And my goal is to give you guys an intuition of how it works, and then go through a working example using GraphLab Create, using a Dado product. So where do you see this? And we all see this all the time, right? We buy things probably from Amazon. And so whenever you buy something from Amazon, you see a list of frequently bought together. So if you are looking at the data mining book, you're often buying another data mining book, and then you're buying a really fluffy book about data science for business. Have any of you read this book, Data Science for Business? What do you guys think? Is it fluffy? Like deep? Did you learn something deep and meaningful about data science by reading the book? No, right? OK. I tried to read this book too, and I couldn't do it. But these other books apparently are quite good. So the data scientist on our team that built this toolkit that I'm going to show you guys, a frequent pattern mining toolkit, Krishna, and I'm using a bunch of his slides, he really likes this book, and he says this book's pretty good too. So it makes sense that these are frequently bought together. So this is a real application of using your log data and mining it for frequent patterns. How about this? This is something that doesn't make sense. And I'm a little scared to say this on a recording, so I'm not going to talk too much about it. But these three items, if you put them together, you can make interesting things. Yeah, so I'll just leave it at that. These are combustible things that come together. And yet this is actually on Amazon. If you look for one, it will tell you the other things that are bought with it. Maybe a data quality thing that maybe Amazon doesn't want to show this, but this is again frequent patterns of things that are bought together. You see this in the real world as well. You always see dip and salsa next to chips. I mean, I guess the idea is also not only are you encouraged to buy these items, but you don't have to go find them, right? No one goes to the store saying, I need to buy salsa, but I don't need chips. So it makes sense to put these things together, because they are obviously frequently bought together. So how do we mine logs? So the first thing is, can we learn some rules and then use that to recommend items? So if you bought coffee and a muffin and a Danish, can we recommend that you should get a donut? So again, you're seeing recommendations. So if you bought this book, you're recommended these other books. So that's different than frequently bought together. That's about the past. So we've seen many receipts that buy these three things together, but you can use this as a way to recommend products as well. So what was bought with this book are these recommended books. So this makes sense in terms of real-world applications. It's not just connecting patterns in the past and showing those. It's also using that to help recommend future behavior. And the final piece is about extracting features. And this is a little bit more abstract. And I think this will make more sense when I go through sort of the demo of this. But the idea is, so you start with raw logs, say in the receipt space. You then want to learn patterns in those logs. And now you're in the pattern space. And by extracting features from the trained model, you can now apply what the patterns have learned from the pattern space into another machine learning task. So a simple way, and my demo gets halfway there, a simple way to think of this is you want, say you're doing your frequent pattern mining, it's unstructured. Now, what the model has learned, you then want to apply in a supervised context. So one way to do that is extracting features from the frequent pattern mining model to then apply in a supervised context. And I'll show you what this looks like. I think it makes more sense than my explanation. So 3 useful tasks when you're looking in data mining. pattern mining, rule mining, and feature extraction. And so I kind of want to go through each of these, give an intuition of them, and then show them working in a demo. So this is pattern mining explained. I'm not going to claim to go that deep. I'm going to give a high-level, somewhat hand-wavy explanation about how pattern mining works, mostly because I don't have the expertise to explain that, but I'm happy to follow up with folks if they want to learn more. OK, so if you have n distinct items, you have 2 to the n item sets, meaning the number of patterns that you can detect is 2 to the n. It's huge for n items. Does this make sense? Because everything can be connected to everything. So the challenge in pattern mining is to find the top k frequent sets of length L, meaning sequence of events, that occur at least m times. So these are three parameters. Top k most frequent sets of at least length L number of events that occur at least m times. So top k is the maximum number of patterns that you want to learn. Length L is the minimum length of each pattern in terms of sequence of events. And min support is if you have a pattern that's of length 4, you only want patterns that exist at least this number of times in your set. Does this make sense? In your logs. So these are the 3 parameters for pattern mining. Of course, brute force is definitely the way you'd start, but it's not going to get you very far. Even with a really small number of distinct items, the number 2 to the n gets you almost nowhere. So you want to follow some basic principles when you're thinking about pattern mining. And these principles will guide the algorithms that approach how to do this. So the first one is to think about something is only frequent if it occurs at least m times. So here's my data set. And so if you think about this, to connect this back to the receipt data that we were looking at before, each row represents a receipt, a completed receipt. And the items A, C, D, these are distinct items. So coffee, cookie, pastry, like that. Does that make sense? So we're looking at each row in this table is a receipt, and each receipt has a collection of distinct items. So we see that if m is 4, at least m times, CD, 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 CD exists 5 times, therefore is frequent. Whereas AD only exists 3 times and is therefore not frequent. Does this make sense? This is the first principle we need to follow. You only have to pay attention to things that occur frequently. Second, so this is the min support parameter that I talked about before. The second one is the a priori principle, that a pattern is only frequent, or a pattern is frequent only if a subset of that pattern is also frequent. So this is kind of common sense, but it's important to think about. So A is not frequent. If m is 4, A is not frequent if you look at this data set. Therefore, anything that starts with A is not frequent either. That's that's pretty intuitive, but that's the idea, because you're going sequence of events, right? Whereas BCD is frequent, therefore CD is also frequent. Okay. So with these 2 principles for doing frequent pattern mining, there's 2 main algorithms for learning patterns in your data. The first is candidate generation, and the second is pattern growth. And instead of going through both of these, I'll just zoom in on pattern growth. Candidate generation is pretty natural to think about. It's a breadth-first search. So let me first talk about the fact that though there are 2 main algorithms, there's lots of generalizations here. And this link is actually really good. It maps all of them and tells you all the tools that you can use that help you with all these different types of generalizations for frequent pattern mining. So if you look at these two algorithms, candidate generation is obviously better than brute force. It has to be, because brute force is pretty awful. It helps you filter candidate sets, but it's negative. Those are the pros. Its con is that it requires multiple passes over your data. Whereas pattern growth has fewer passes over the data and is more space efficient. So I didn't mention it, but top K, FP growth, is what we have in GraphLab Create. So that's what I'm going to show you in the demo. So let's go through pattern growth. And again, my goal here is to give you an intuition of how it works, not to get to a proof that all of us understand together. I think at 7 p.m. at night, it's pretty hard to get through any proofs. At least it is for me. But if you think about the algorithm for pattern growth, it has two main phases. You're filtering candidate patterns, and then you're constructing a new database of a conditioned database based on the filtered candidates that you have. And then you're recursing. You're doing that again. So this allows you to avoid full scans, as I'll show you pictorially through a few slides, and it prevents you from having large candidate sets. And this is alternate to the candidate generation approach, where because it's breadth first, you're generating, you have large candidate sets, and you have to keep going through your data over and over again. Here we go. Pattern growth pictorially. So remember, this is our data set. These are each receipts of distinct items. And what you're seeing here is there are 6 entries if I'm looking at the overall data set. So A exists 3 times in the data set. B exists 4 times. C exists 4 times. D exists 6 times. Because M is 4, remember M was 4 in the previous slides, we're sticking with M at 4, I can exclude A altogether. That's principle 2, the a priori principle. Actually, sorry, this is principle 1. If you're not frequent, then I don't have to consider you or anything else that comes from you. So we start with 6. We start with the empty set, and then we count. We go one level deeper. We count all the instances of A, B, C, and D, the distinct items in our set. And we exclude A because it's not frequent enough, and we go straight to B. So once we're at B, we now look at B's children, and this is where we enter the first growth. So again, I've just taken this part of the tree, and I've drawn it here, and I've taken this data set part over here, and I've enumerated it here. So what you can see is this DB, and I know this is confusing, this DB represents the database, the conditioned database of frequent patterns. And right now, the database with no conditioning is your whole data set. So far, so good, guys? This is all going to make sense in like 3 minutes, I think. And if not, I want you to stop me. So the next thing we want to do now is construct the next, to construct the conditional patterns that exist conditioned on B, because that's the node we're exploring in the tree. So what does this mean? This means from my data set, my previous construction, my previous database, let me find all patterns where B is a predecessor. So we see that BCD, BD, BCD, and ABD, B is a predecessor to D, so I include D. Does this make sense? So I've pruned out these other data sets. So now that I've done this, I can filter these candidates. Remember the 2 phases of this approach. You filter candidates, then you generate conditioned candidates, and then you filter them again, right? And so, let me go back. So what you see here is now I'm looking at this. I see C is only there twice. Now it's not frequent enough, so I can drop it. But D is included 4 times. So I add BD as frequent. So BD now matches my criteria as a frequent pattern. So then we go back. So now we're looking at BD in my tree. My next step, so now we're here again. Now we're conditioned at dB of B. This is what I see. And I'm looking to see, are there any entries in my logs that have BD as a prior, as an event, as part of a sequence. And it turns out there isn't. So all of the remaining entries in my condition database, none of them start with BD. So that means I'm done. So that means I don't need to explore anything further. I'm now done with BD. BD is frequent, but there's no further patterns from BD. Does this sort of make sense, this tree walking that we did? It's a depth-first approach to growing the patterns that exist in your data. And essentially, you're pruning and growing, and this way, you're much more efficient. You're not having to do full data set scans with each pass. Now, to make this even faster, there's a data structure called the FP tree, which makes this quite elegant. This makes it easier to traverse through this tree structure. So this is very similar to a trie data structure, the TRIE, where you can see that I have connections to my siblings as well. So this is a data structure that we use to make the pattern growth algorithm more efficient. And then there's an optimization on this. So again, this is pictorially done from FP growth with candidate filtering and conditional databases. So if this is where we start, we're able to, the paths containing node C, and then paths containing node E. That's, I don't know how to say it. I'm not going to describe it well, but it helps you navigate the tree for the two phases of the growth algorithm. And finally, there's an optimization off this called the top K FP growth. This is what we've implemented. It's very similar to FP growth. The same intuition applies, but it allows you, it works by dynamically raising min support and allows you to specify estimates of min support, so it's not something that has to be learned. And this can give you really great results. So let me give you an example. So if we're looking at website log data, say I have 1.5 million events that span 84,000 sessions with about 3,000 unique IDs. 3,000 unique IDs, this would be distinct items in the previous analogy with the coffee shop. So how long does it take if I'm learning if I just use top K, so that top K without specifying min support versus with min support. So just using top K, as I'm at 25,000 K, and remember K is the first parameter, which, help me with this, guys. K was the maximum number of patterns to detect. So K is the maximum number, L is the length, and M is the minimum support. So with K set to 25,000, so find me 25,000 patterns, this is taking 30 seconds. Whereas if I set min support to 2,000, saying I only want if I only want to learn patterns that have that occur at least 2,000 times, then you can see how much faster that is. That's what, less than 15 seconds. So more, it finishes in less than half the time. Does this make sense? It intuitively makes sense, right? You don't need to learn all the patterns. I only care about patterns that occur this many times or greater. And so by specifying that, you reduce the problem space quite a bit. OK. So why don't we do this in code? That's probably a little bit easier. Is this a reasonable intuition about how frequent pattern mining works, how the algorithm works? Obviously, there's a lot more detail, and there's a lot more you can learn about this. No way I could cover all of that in this late in the evening. OK. So let's clear all of my output. And then let's make this a little easier to read. OK. So you guys can read that, yeah? Can I actually make this a little smaller? Can you still read it if I make it? Is that too small? Is this OK? OK. No? First one's better. It's like we're at the eye doctor. Like 1 better, 2 better. OK. So we'll toggle the header. We'll get rid of the toolbar. We can even go full screen to get rid of some of the extra white space. OK. So everybody here is familiar with IPython Notebook or Jupyter Notebook? Yeah? No? OK, good. So I'm not going to have to cover what this is. So we're using GraphLab Create. GraphLab Create's a Python library. So like everything else in Python, we start by importing GraphLab. The next thing we want to do is load our data set. So this is a bakery data set that I've saved as an S-frame. An S-frame is a scalable tabular data structure, very similar to a pandas data frame or an R data frame, but it's an out-of-core data structure, so you're not limited by RAM. So unlike pandas, where the data has to fit into memory, with the S-frame, it doesn't. And this is a data structure that we've open sourced as part of Dado. You can download it and run it separately from GraphLab Create. And you see that this data set looks very similar to the slide that I had before, where I have line items of items sold associated with a receipt, an employee, a date, a sales date, store number, and the quantity of those items sold. You can also see I have 266,000 rows. So this isn't a huge data set. I want this to work on my laptop in interactive speeds while we're talking. So I can call .show, and this brings up GraphLab Canvas, and it gives me a sense of my data. So if I want to look at the histogram of which items are bought most frequently, just in general, a coffee eclair is the most common item. It's been bought 3% of the time, followed by hot coffee, a Thule cookie. Does anyone know what that is? I have no idea. OK. Cherry tart, I know what that is. Strawberry cake, apricot Danish, orange juice. Orange juice. Huh. OK. And on and on. So you can see that this is the frequency distribution of items that have been bought in this data set. This by itself is kind of useful. This is why GraphLab Canvas makes this easy to do. But let's go find some patterns. So all of the models in GraphLab Create are exposed as toolkits. So you can tab over and look at all the different toolkits that we have. And so we have toolkits that make it easy to train lots of different types of applications. And so I don't need to cover all of that. But today, we're going to look at pattern mining. That's the toolkit that we're going to use. And so if we tab over, we have one model, frequent pattern mining. You can see this is the actual model that gets trained, a frequent pattern miner. Create is how you train that model. And get default options, it tells you what are the default options for this model. So if I look at the docstring for the create method, which trains the model, can you guys read this? You can see that my parameters are a data set, an item, so the name of the column that represents the item that we're going to use. And so the item must be string or integer. And then the list of features that you want to apply. Then you can specify min support, max patterns, and min length. Remember those 3 parameters that we talked about in the slides. All are there, but they're optional. So, and we've got great references, so you can read more than what I just talked through. And we've got an example that you can run directly, which happens to be the same example I'm going to run. So here, I'm going to call that constructor, frequent pattern mining dot create. Pass in this data, the table that we just loaded, the one that we just called .show on. We've called it SF. We're going to say the item column is called item. And the features we want to use for mining, for finding patterns is the receipt feature and the store number feature. And our minimum length for a pattern is 2. So just to think about that, that means that we're looking for patterns where people buy 2 or more things. And we want to only look at receipt and store number as features to consider. The date is not something we're going to look at. Does that make sense? Or the employee ID, which sort of makes sense, right? OK, let's run that. So there are 50 unique items in the data set. And the model found 75,000 unique transactions. So you can see how long it took. 36 milliseconds. And we found 100 closed patterns, unique closed patterns of minimum length 2. OK? So This is all happening on my laptop. I'm not sure if I made that clear before. And my laptop is in no way special. It is a Dell computer that you can buy today. And I mean that, in no way special. And I'm running this whole demo on Windows, which is also kind of amazing. So GraphLab Create runs on Windows, on Linux, on Mac. OK, so what do I do to get the patterns? I just call get frequent patterns. This returns me another table, another S frame with the patterns. And then I'm just printing them out and saving the model locally. But printing them out, I can see the most common pattern of two items that were bought together is the cherry tart along with the apricot Danish. So I guess that's neat. Followed very closely by this cookie I don't know. Is it Tweedly? No? No one can help me? No one knows what type of cookie this is? Oh, man. And a marzipan cookie. But you can see there's a pretty big difference in terms of how frequent these patterns are compared to all the other patterns. So these two are 3,800 or 3,900, almost 4,000 repetitions or in the data set versus the next one, chocolate cake and chocolate coffee. What is chocolate coffee? Anyway, maybe that's a mocha. Maybe that's what they mean. Chocolate cake and chocolate coffee is at 3,300. So we've now identified our patterns. This is good, right? So now we can do the first real-world application. People who bought this frequently bought this other thing. So essentially connecting the past to find the pattern. But let's use this to actually make some recommendations. So how do we do that? Well, this model's trained, so I can just pass it new data. So I'm going to create a fake receipt. So I'm going to say there's 2 line items. And this is kind of cryptic to describe. But this is what we're creating here is an S frame with 2 rows in it. And actually, I'm going to break this so that you guys can see what this looks like. So let's go new data. Actually, why would I type it all again when I can copy and paste, right? So we'll do that, and we'll look at new data. So what I've created is an S frame with 2 rows in it, same receipt number, same store number, and 2 items. And this is all I need because I discarded those other features, right? So my model doesn't know about sale date, employee ID, so I don't need that input if I'm asking for prediction. And now, to get some predictions, I can call predict, pass in this new data, and I can predict that I should sell apricot Danish to for the person. If you bought cherry tart, I'm going to recommend apricot Danish. Does that make sense? It's also a pretty neat example. This also reinforces what we saw here. Cherry tart and apricot Danish are the most frequent pattern in our data set altogether. So if you buy cherry tart, of course I'm going to recommend apricot Danish to you. That's what I've just learned from mining my logs. So now I've got a recommender that's based strictly on my log data. Pretty good, right? Now let's. Is this real data? I don't actually know. I should find out. I think this data set is a real data set, but I don't know from where. Yeah, I think it is real data, but I don't know from where. I also don't know where you can buy an apricot Danish anymore. But that could also be because I don't go to fancy coffee shops. So who knows? OK, so let's predict a top K instead. So what instead of just predicting, which would give me the highest prediction with a confidence score, what are the rest? What are the other things that I could be recommended for this input data set? So if I see apple pie, I could recommend coffee eclair, almond twist. If I see cherry tart, I could recommend opera cake. If I see apple pie, I could recommend both an almond twist and a coffee eclair. But you can see the confidence goes down for all of these. But again, it's not just predicting the next thing, but you can also predict other things. And so that's what the top K helps you with. What are the top K predictions given the patterns that I've learned? And then finally, I mentioned extracting features. So far we're in the pattern space right now, right? We know what are the patterns that I've mined from my logs. That's what my model has told me. So I now see the most frequent patterns, but how do I apply that into a different context? So the simplest way to do that is you want to extract features from this trained model and now look at those extracted features which you can then apply into another context. So let me show you what that looks like. So we call model.extract features, pass in the same receipt data set that we started with, SF, and now you can see what I have instead. So my extracted features, I have the receipt number, the store number, and I have the, from the pattern space, a numeric representation, so a vector of floats that represents the pattern. So not interpretable, not nearly as interpretable as looking at the pattern itself, but I can now use this in a totally different context. And this is as far as my demo kind of fizzles out now because I didn't get to a point where I really feel great about what I'm doing. But the place I was trying to go and I didn't quite get there is, OK, I now see patterns of things that are frequently bought together. Now let me find out which of my employees is really good at upselling. Hey, you bought that apple tart. You really want that apricot Danish. I want to find that employee, right? So that's a different task. So can I do that? So I'm going to start by trying to cluster in my employee space instead. So that's just a group by. If you remember, my data set is each item purchased is its own row. Well, that's not actually what I want to do. So I want to group by employee ID so I can see. So essentially, each receipt is now just one row. So now you see that I've done that, and so I have receipt number, store number, and employee ID. So now I have employee ID per receipt. And now I'll join this against the pattern, the extracted pattern S-frame that I just had. I'm going to group by the employee ID, and I'm going to sum the extracted features. So summing across this vector is going to do an item-wise summation between each of the extracted features. So just to make this a little bit more clear. So if I was summing if I was summing from here, if I was summing this and this, I would get the sum would be 1, 0, 1, 0, 0. Does that make sense? I'm going to do item-wise summation. And I want to assign that to a new column that I'm going to call all features. So I'm grouping by employee ID. I'm joining the employee table that I just created with the pattern table, grouping by employee ID, and aggregating and summing the extracted features that I extracted from my frequent pattern model. So now I can see employee 47 has this summed all features. So these are the patterns of things that were bought by employee 47, 40, 16, 23, and on and on. And this is kind of where I stopped. This is as far as I got. So my next thought was, let me cluster these guys. And I started with clustering, saying there's 3 clusters. I'm not entirely sure. And so go ahead. We can go ahead and do that. So you can see how easy it is now that I've extracted the features. I'm in a different space, so it's way easier for me to do other tasks like clustering, or nearest neighbors, or any other machine learning task where I don't have to think in the pattern space anymore. So I've done this. Now let me show the cluster IDs by employee. So again, by employee, we see that employee 47 is in cluster 1, cluster 0 for employee 16. And finally, I just went to represent this as a bar chart. And so by cluster ID, my Y value is store number. So I think what this tells me, and this is where I'm not thrilled by this, but I think what this tells me is that cluster 1 is doing a much better job of selling patterns. Now, So the goal of this, the bottom half of this demo, is to show how extracting features can be useful. I'm not convinced I actually found a useful conclusion, but hopefully I've still demonstrated that this is something that's useful to being able to extract features from a frequent pattern model is a useful thing. And so what's the summary here? log data mining is not rocket science. Of course, I couldn't talk about it if it was. So FP growth is a great algorithm for finding frequent patterns. You, by finding the patterns, you identify rules that you can use for making predictions. We showed that. And then finally, you can extract features which can help you do machine learning in the pattern space. And I really didn't get there far enough, but I hopefully got you thinking that this is something that's worth trying. So that's it. Thanks, guys.
Questions?
Okay, so you mentioned your background is in distributed computing, so I'm actually quite curious at what points in the sort of the data graph lab atmosphere distributed computing is used. Like, could it be used for FP growth? Is it used to parallelize S-frame based computations?
Good point. Great question. So short answer is yes, distributed FP growth is possible. It's something that we're planning on working on. It's on our roadmap. It's something we're moving towards. We first wanted to make sure that we had a great single machine implementation of the algorithm, and now distributing it makes sense. Distributed S-frames also makes sense. A little trickier to do, but since S-frames are immutable data structures, absolutely possible. And obviously, distributed machine learning is, we have several models already implemented with distributed implementations. So the mentality that we have as a company is, let's make sure that we'll only run something in a distributed setting if it's strictly better than the best single machine implementation. If you don't require the data to fit into RAM, then you can get so much more done with one machine that you only want to go through the effort of distributing if it's going to be better than the best single machine implementation. Does that make sense? So, and I say better, not only faster, but without sacrificing convergence rates or accuracy.
Yeah, I guess kind of makes sense. I mean, anything that's parallelizable could be better if you have a lot of machines. Now, if you're willing to pay for extra cycles, obviously.
Well, yes, but what I'm going to challenge you on there is not if you're going to give up accuracy. And a lot of distributed implementations do give up accuracy. And not if you're going to lower convergence rates. So if you have to run 1,000 extra iterations to get to the same test error, same training error, then that's not necessarily good. So we sort of say, if you can get it done on one machine, then you have to be strictly better than that if you want to distribute. It's a great question. Any other questions, guys? Yeah, go ahead.
From your experience, any rule of thumb to determine the minimum support?
Yeah, so the question was, any rule of thumb for determining minimum support?
Actually, all of those, like
All of the parameters. So the question was, what's a good guideline for determining the parameters for frequent pattern mining? This is one of those cases, like a lot of things in machine learning, where it's very application specific. So what's the pattern? So for this example, right, people aren't buying 50 things from the coffee shop, because chances are what you're buying from the coffee shop, you're carrying out in your hands. So that should influence your decision on what are the length of patterns that you're looking for. Whereas something like website logs, depending on how well instrumented your site is, an average session. So this is one of those things, I'd use some aggregate statistics in general to help me set these parameters. That's probably the guideline that makes the most sense. So what's my average session length, average number of events per session, then let me go through one flow that a user might have. So get to the website, log in, go look at their account page. So I'm making stuff up, but there's probably a flow that you can imagine which results in X number of events. So let's set that as min support and see where we are. Or set something higher and see if the patterns that emerge are useful and then go backwards. Obviously experimentation is important, but this is a data set with 266,000 rows, and we're at 36 milliseconds to find things with min support at 2. So again, if it's fast, you might as well experiment to try a bunch of different things. Does that help?
Yeah. Can I ask one more question? So in the feature extraction, is
Yep.
there like physical meaning for that feature extraction number?
Is there a what?
Physical meaning?
Oh, a physical meaning. Not a good one. I mean, I think the best way to think of it is it's like a. I guess the way my understanding is, I think of it as a thumbprint of the pattern. In the pattern space, give me a thumbprint of this pattern.
So
But
there's a follow-up question then. What's kind of like distance metric used to determine the cluster?
right. So k-means, I believe by default uses. I think it's Euclidean, right, Sean? Yeah. Okay. Good. But you can tune that, so that's something you could set.
My question, like basically, if you like how to determine the distance metrics, that's basically based on what kind of like feature the feature you extracted, right?
That's right.
So it's hard to say for what kind of recall.
No, it's a good question. It's one that we should follow up on. I'm pretty sure our documentation does explain in more detail how feature extraction works, and it's something that I should read and know better.
Thank you.
Yeah. There's another question up front, and then in the back. I'm happy to repeat the question so you don't have to run around with the mic. Go ahead.
I was just going to ask, does the algorithm that you guys developed handle order? And it seems like it handles unordered. Does it also handle order?
When you say ordered versus unordered, do you mean sequence of events?
Correct.
So the sequence is the pattern. So yes, but not, how do I say it? Yeah, so it is ordered in that sense. Does that make sense?
Okay, and looking at the data, it looked like maybe it wasn't, but I obviously don't understand.
Yeah, the intent is that you found a pattern of events that happen in order, and that's what you're learning.
Thank you.
Yeah, in the back?
I have just one quick question.
Sure.
Suppose I buy an item that you don't have any. Alright. So suppose I buy an item that you don't have any frequent pattern for
Yep.
that item. So what is the solution? Or in other words, suppose I buy an item and you need to recommend me at least 5 items, 5 new items, but you don't have too many frequent patterns for that specific item. So again, what?
Well, it's a good question. So if I don't have frequent items to recommend you, I could always recommend most popular items. So the most popular sold items, it's pretty standard default for recommendations. If I don't have history for you, or the item you bought hasn't been bought frequently, it's a new item, I can just show you popular. You could do something a little bit more sophisticated. If it's a new product, can I define a distance? Can I find similar products to this one, where maybe I'm using a composite distance function to build a nearest neighbor's graph, and then okay, this product that's brand new doesn't have I have no patterns for it yet, but if I can find the most similar product to it, maybe I can use recommendations for that product as a proxy. So there's a bunch of different techniques. It's the same cold start problem for most recommendation systems. I don't know you, or the item is new. What do I recommend?
I was just wondering if you came up with any innovative solution to address that problem.
So innovative solutions for this problem. So I think I just talked through a couple. The most simple is just popular. What is the most commonly sold item? I'm going to recommend those.
Yeah, but for some cases like Amazon, so that doesn't exist. So there are millions of items. So when I'm like, oh, cheap, you cannot recommend me.
That's totally true. So that makes sense if your items are very different. But then chances are you have some degree of organization of your products, maybe departments or categories. And now you can define, that can help filter your popular items to say most popular items in automotive, and then I'm showing you that. But honestly, I would definitely explore the idea of finding similar products as proxies, especially if it's a new product, right? So if I can find a lookalike to this product, my cherry tart is probably close to an apple tart. And if I've only started selling a cherry tart, but I've been selling apple tarts for years, let me find the recommended products for an apple tart and recommend those for a cherry tart.
Thank you.
Question in the front, yeah.
What's one of the coolest
what's one of the coolest customer deployments you've helped implement?
Sure, good question. It's awesome. It's awesome to ask the sales guy about customer deployments. So first thing, we're not a services company, so we don't actually do deployments. We don't sell solutions. We sell software licenses. And so I think you're asking me is, what are some of the cool apps that our customers have built? Cool is a tough one to meet because I'm pretty boring as a person.
What's interesting to you?
Interesting to me. Why don't I talk about one that's log related or data related, data quality related? I can talk about data matching. So Zillow and Practo Health both use us to improve the data quality of their data by leveraging our deduplication and data matching toolkit. So this is record linkage. And so this is pretty close to logs. Maybe not as sexy as using deep learning to classify how full a dumpster is, which is what Compology is using us for. But I think it's a pretty cool application because it's just like logs. Everybody has lots of data sources. You probably have duplicate data, and you probably can leverage record linkage or data matching to help develop a best truth if you don't have a ground truth in your data. So how's that for a couple examples? I have lots of others. I can go through a whole use case set of slides, but I don't want to do that. But I'm happy to follow up afterwards to talk more. Yeah, go ahead.
Actually, just wanted to follow up on the question about ordered versus unordered.
Yeah.
In the depth first search that you showed us, it definitely looked ordered, like you're basically finding a sequence of events,
Yep.
One after the other. But the coffee shop example in real life is probably more like an unordered event in that
Yep.
I didn't buy, on a given receipt, I didn't
Yep.
buy the apricot, whatever.
That's right. You're right. Totally.
I can think you could get into trouble about that if you had a cherry tart and an apricot tart, but then also apricot tart and cherry tart.
Yep.
Because you're treating it as ordered structured data, and
Right.
those two in our mind should actually be viewed as the same.
Right.
But the depth first search would not match on that.
That's a good point. That's a really, really good point. And I guess that I should use a different. It's a really, really good point. So receipts don't have an order because you bought all those items at the same time. So there's no order in the receipt. And yet the idea of frequent pattern mining is to find ordered events. So I guess maybe one way to say that is we're finding patterns of items that were bought together, not necessarily in a sequence of like you bought this and then you bought that, but more that these items were bought at the same time.
Maybe you could be diligent with sorting up front or something.
That's right,
Make sure
yeah.
the apricot tarts and A's are always there, so you never have a case where
That's totally true. Yeah, you could say that.
the group by just has to get a little bit more specific.
That's right. Yes. That's great. Good point.
It seemed like your algorithm had to do 2 passes anyway.
Yeah, you can't get away with just one pass, but you have less passes than having to go through your whole data set multiple times.
Right, but the order issue is kind of taken into account by the fact that you're doing an initial pass. So you're ordering them like you did it.
That's right.
Actually works.
Right.
So
Oh, I see what you're saying. By multiple passes, I am sort of handling, as long as I'm being systematic.
Apricot and then a Danish.
Right.
And then someone else bought a Danish and then an apricot is 2 separate things. So
Right.
you did an initial pass, and you ordered those items. How was your ordering?
Right. Thank you. Was there another question? Yeah, go ahead.
So with depth first search, one of the problems you usually run into is the recursion limit. If you recurse the function so many thousands of times, it might run out.
Below the stack, right? Stack overflow, right?
Exactly. So I assume with the the minimum length, you're looking for a minimum depth to search for. You also have like a maximum depth to search for in things, and would that limit the size of the graph that you can process?
That's a good question. So the first thing is think of recursion not as an actual implementation of recursion, but as the algorithmic, the way to think of the algorithm. By leveraging the FP tree, we're not actually recursing. Does that make sense?
Yeah, that's fine.
So there isn't a Stack Overflow issue that I'm going to blow the stack because I'm essentially putting more and more things on my stack frame. So we don't actually have that limitation of recursion. It's more that algorithmically we're recursing in that we're growing filtering, growing, filtering, growing, filtering. The implementation is iterative. That's a great clarification.
Question more about your products. I see that your product is great for more like graph-like algorithms. Can you comment a bit about your products for non-graph-like algorithms?
Yeah. So that's a great question. So the question was, so do you guys do more than just graphs? And the answer is yes, we do. Graphs is just one thing, one type of machine learning. We're a full broad machine learning platform. So we have models in basically all of the basics you'd expect. Linear, logistic regression. We have all the tree models, random forests, gradient boosted trees. We have convolutional neural nets, so deep learning. Nearest neighbors, which is you could think of as a graph. Matrix factorization, all the recommender models, including factorization machines, which is a really complex model. So we do a lot more than just graphs. Of course, we have graph analytics as well. So PageRank, connected components, triangle count, label propagation. So yes, we do a lot more than just graphs. There's another question. Yeah.
Sorry, it may not be related to this field, but in finance, assuming that we want to use this concept to do anomaly detection, we have a bunch of continuous variables for like 500, 600 stars, lots of time series. Which approach among those three that you mentioned is more useful to learn something from these time series to do the anomaly detection, and which resources do you think we can use to learn more from those signals?
Yeah, great question. So the question, how would I do anomaly detection or outlier detection on time series data? So first, we're building an anomaly detection toolkit. It's coming, hopefully by the end of the year. In fact, the primary author of that couldn't make it tonight, but he's in New York with me this week, Brian Kent. So we are making it easier as a high-level toolkit, but to do it today, the kind of standard approach that I'd go with is you want time series support, which we have in GraphLab Create. So time series, think of it, it's built on top of the S-frame. Think of it as an indexed S-frame for time series data. So outlier detection, you want to have a rolling average over a time period or a number of data points. And then say 2 standard deviations outside of your rolling average. Anything outside of that is an anomaly. And so you want to be able to detect that as you're going through data. So you could do all of that today, and I've got a crappy demo that I'm happy to share with you in terms of doing that all with our tool today, but we're making it much better with an anomaly detection toolkit that's coming soon. So, but that's a standard approach, right? Rolling average over a window of data, and then look for 2 standard deviations off that rolling average.
I'm a Python programmer, so I guess for me the most famous machine learning platform is scikit-learn.
Sure, yeah.
So, what are the advantages of your platform compared to that? Like, powerful or you provide more machine learning algorithms?
Sure, good question. So how do we compare to scikit-learn? 2 main things there. Scikit-learn has a ton of models, and fundamentally, you need to not only represent your data in matrix form in order to use scikit-learn, you really have to, I think of scikit-learn as a very low-level tool. So you have to know all the hyperparameters, you have to know all the notation that goes with the paper that was implemented in implementing that model. And so that makes it a little tougher to start. So if you're not a machine learning person like me, it's much harder to get started with scikit-learn because I have to first turn my data that kind of makes sense to me. It's receipt data, for example. I have to turn this into some matrix representation, and then I have to set a whole bunch of hyperparameters that I don't understand, and I have to know which model I need to apply. So if I'm building a recommendation system, I have to know I want item similarity or matrix factorization. There's nothing that guides me there. Whereas with GraphLab Create, you don't have to think in matrix terms. You saw that we used our raw data, plugged it directly into our model. B, you saw the toolkits, so the models are organized as toolkits. That makes it easier to get started. And then C, hyperparameters have sane defaults, so I don't have to know about them ahead of time. I can get started without having to specify them. You saw that with the frequent pattern mining toolkit. Those 3 parameters we went through, K, L, and M, they're all optional parameters. So the idea is with our tools, It's easier to get started. Your data can stay more in its natural form. And then the third reason that's also obvious is scikit-learn relies on NumPy. NumPy requires the data to fit into RAM. With GraphLab Create, because the S-frame is an out-of-core data structure, that's not required. So now you can work on terabytes of data using your laptop, which is impossible to do with scikit-learn. Love to follow up more and talk more about that. How do we compare to Spark? Spark is an amazing project. We love it as a distributed data engineering platform. So Spark is fantastic for turning petabytes of logs into terabytes of useful data. Where Spark is weak today is on modeling, on actual machine learning. They have a limited set of models. All their models run in a distributed setting, which often means that they're sacrificing accuracy and performance versus our implementation. So where we shine is on machine learning. Where Spark shines is on data processing. So we integrate really deeply with Spark. So we read the Spark data structures, the RDD, schema RDD, or Spark data frame natively. We published a Spark package a couple months ago. So if you have a data engineering pipeline that's written in Scala, you never have to drop into Python to convert your RDD or schema RDD into an S-frame. S-frames are more efficient for machine learning. That's why we wrote the data structure from scratch. But you can also interact with your Spark environment through PySpark, and we play really nicely with that. So I don't think of it as comparing, because MLlib is a much newer research project. It offers much less than what we offer. But these are complementary tools. If you're already using Spark, then GraphLab or Dado fits really neatly into your Spark environment for modeling, for machine learning, and for going to production. Yeah, go ahead.
So once you're in a data set that's outside of RAM limitations,
yeah.
what kind of performance drop do you start seeing? If you go to main memory, you're probably seeing a lot.
So the question is, how does your performance drop once you're out of core? And the answer is, we're faster than scikit-learn, VopalWabbit, libffm, libsvm, even when you're on disk. And that's because of the S-frame. It's because of the data structure, thinking really carefully, having a columnar architecture, and being really efficient with how we store data with a lot of compression techniques. And then down to the actual model implementation, being really careful with how we access memory. So unlike most of the other machine learning tools, they just assume all the data's in RAM, so lots of random access. So once you're on disk, you don't want that. So we are really careful about making sure we have sequential read patterns for getting through the data. Does that make sense? So we're really, really careful about optimizing this, because absolutely, it doesn't make sense just because you can work on bigger data. If you're that much slower, then it's not worth it. You might as well go on a bigger machine. But the other thing that we can do that some of the Python tools can't is we eat up all your cores. So we have a Python API, but our engine's implemented in C++. I didn't get into that too much in the demo, but once you start actually using our engine, the C++ process is invoked. That's running on all your cores. It's going to eat up all your RAM and then spill to disk.
Maybe one more.
Who wants the last question? Come on. One more. I should also mention, why don't I, if you guys have asked me so many great product questions, I should plug Dado. So our whole product, everything we've done that I've shown you tonight is free to try. You go to dado.com, register, you can download, get started, find all the bugs in my demo, email me, tell me about them, and then I'll make them better.